Hi everyone, and welcome to the start of a new unit. In this unit, we're going to look at exponential functions and the inverse of exponential functions. Today, we're focusing on exponential functions and their graphs. So an exponential function is defined as y equals a times b to the x. You can write it with a multiplication dot or with parentheses, either way you want to look at it. This is a more basic form of an exponential function. By definition, a function is exponential if the input variable is in the exponent of some base. Here, a cannot be equal to 0, b has to be greater than 0, and b cannot be equal to 1 for it to classify as an exponential function. Unlike all of our other parent graphs we've studied this year, the exponential function does not have just one parent graph because b could be a variety of different things. We could be looking at y equals 1/2 to the x. We could be looking at y equals 3 to the x. There are an infinite number of possibilities for that base, so we can't just say, yes, this is the parent function for every single exponential function you'll meet. But we can say that this table, and we only use 2 points in our parent table, works for every really basic form of an exponential function. So if we input x, anything to the 0 power, so b to the 0 is equal to 1. So our output would be 1. So the point 0, 1 is always on the parent table of an exponential function. And if we input 1 for x, we get b to the first power, which is just equal to b for our output. So our parent table looks a little bit different than we've used in the past, and it depends on the base of the exponential function. Exponential functions also have something called an asymptote. It has a horizontal asymptote at y equals 0. What that means is there's a dotted line at y equals 0 that our graph approaches but never touches. It gets closer and closer and closer. It cannot cross through or touch the horizontal asymptote. The domain of any exponential function is -infinity to infinity. And the range of any parent exponential function is 0 to infinity. But because we can never touch that 0, it is not included. And that's the first time that we are actually dealing with range of a function that doesn't have an included value as an endpoint. So to repeat, an asymptote, that's a new term for us. It is a line the graph approaches as x or y increases in absolute value. You can never touch it, you can never cross it. Exponential growth in general, when b is greater than 1, we are going to start out very small, getting bigger and bigger and bigger until eventually we shoot up, creating this kind of elbow shape. Now, exponential growth will not cross my x-axis. There's a dotted line here that elbow shape is never going to cross or touch. That's my asymptote. Exponential decay happens when your base is in between 0 and 1. Remember, your base can't be negative. And that means that we start out at a very high number, but then we're getting smaller and smaller and smaller and smaller. Like if you think about cutting something in half over and over and over again, you're never going to quite reach that 0, but your piece is going to get quite small. Again, we have an asymptote here that we kind of sit on, but we never actually touch. So you do need to be able to recognize if you're drawing an exponential growth shape or an exponential decay shape from your original problem. So here we are, our first example of an exponential function we need to graph. We look for the base of the function. The base of the exponential function is not a transformation. It helps us with the parent. So the base of this exponential function is 3. Obviously, our x is in the exponent of that 3, so therefore it is the base. So our parent function is actually the really basic version of y equals 3 to the x. you pull the base, and then you put it with a plain x, everything else is going to end up being one of our transformations. So once again, you're learning about a parent and applying knowledge you already know about transformations. So we start with that table. We had the point 0, 1 and 1b, but our b is equal to 3, so this parent would have this parent table. We also need to carry our asymptote with us because depending on our transformations, this asymptote can shift in our coordinate plane. The way we handle transformations on the asymptote is if we change any of our y's with our transformations, we also have to consider changing the asymptote because the asymptote is a y value. The parentheses are kind of hidden in an exponential function. And they're kind of hidden up here in the exponent. So anything happening to x in the exponent is considered the inside of the function, or your horizontal transformations. Everything else is an outside transformation. So this first transformation, we have to move left 4, and we use our table to do it. To move left 4, we subtract 4 from all of our x's, leaving the y's alone. That is the only horizontal change we have. Remember, 3 is your base, so it's not a transformation. The next one would be this 1/2 on the outside here. That is a vertical shrink by 1/2. In order to do that, we multiply all the y's by 1/2. The x's don't change, so we have 1/2, 3/2, 0 times 1/2 is still 0. We have a negative, which is its own reflection. Don't try to group it together with something else. Let it be its own entity. So a negative on the outside means we reflect the x-axis. In order to reflect the x-axis, we multiply all of our y's by -1. So we have -1/2 and -3/2. 0 times anything is still 0, so you would leave your asymptote as y equals 0. And then we have a last transformation on the end, +6, which means move up 6 units. So we get 5.5 and 4.5 when we add 6 to our y's. And we also need to remember to add 6 to our asymptote, which is a y. 0 plus 6 is 6. The first thing I graph on my coordinate plane is actually that asymptote. Y equals 6 is a horizontal line. Asymptotes show themselves on the graph as dotted lines. I plot my 2 points, -4, 5.5, and -3, 4.5. There are my 2 points. Now the shape we have to think about a little bit. Because my parent is y equals 3x, 3 is greater than 1, this is an example of exponential growth. So if we think about really basically, the parent of this function is going to look something like this. But in here, I shifted left and stretched it. I reflected over the x-axis. When I reflect over the x-axis, thinking about just this general shape here, all of a sudden, now my shape is going to look like this. So there's some reasoning you need to use when you have your 2 points. So I know my exponential growth shape reflected about the x-axis looks something like this. I need to go through those 2 points, so I get really close to my asymptote, and then I kind of shoot off to -infinity, creating an elbow shape exponential growth graph there. The domain of any exponential function is -infinity to infinity. The range here, I have an arrow pointing to -infinity, my lowest y, all the way up. We're getting super close to that asymptote 6, but we're never touching it, so it actually has a parenthesis. And there we have the graph of this big, complicated, long exponential function. So here the parent takes our base, 1/3, raised to the x. We create our table, always has a point 0, 1, and then 1 comma base, so 1 1/3. Always start your parent with the asymptote of y equals 0. There's nothing up in the x up here, no transformations happening in the exponent. Therefore, we don't have any horizontal changes. The first change we need to deal with is this 2 on the outside. which is a vertical stretch by 2, meaning we take our coordinates, leave the x's alone, multiply all the y's by 2. The last transformation is minus 3 on the outside. That means we move down 3. In order to do that, we take our table, keep the x's, subtract 3 from all of the y's. So we get negative 1 here, and we get negative 2 1/3 here, with an asymptote that's now changed to negative 3. The first thing I graph on my coordinate plane is the asymptote, y equals negative 3. I plot my 2 points, 0, negative 1, 1, negative 2 1/3 would look like there. My exponential decay shape looks something like this. We start out really big and then we get really, really, really small and close to my asymptote like that. I knew this was an exponential decay because my base was 1/3, which is a fraction in between 0 and 1. So in order to graph exponential functions, you need to have some awareness of, am I starting with the exponential growth graph or the exponential decay graph? And then you also have to kind of keep track of what your transformations are doing to that graph. The hardest part about these is really any reflections. The other thing we need to discuss in this note session is how to write exponential equations using a set of coordinate points. We substitute in the coordinate points to create a system of equations, solve the system of equations, and record your final equation. So when we are solving, what we're solving for is a and b. We remember the most basic form of an exponential function, a times b to the x. Our parent always has a equal to 1. That's why we don't write it down. So we're going to use this general form in these 2 points to find an exponential function. So our first point, if we substitute in, we get 6 is equal to a times b to the first. Our second point, we get 24 is equal to a times b to the third. We would take one of our equations, solve for one of the variables, and substitute into the other equation, one of our system of equation strategies. So I'm going to take my first equation and solve for a. The way I'm going to do that is by dividing both sides by b. I find out that 6 over b is equal to a, solving a literal equation. And then I can take that and plug it right in here. So 24 is equal to something instead of a times b to the third. Well, this is 6 over b from our work over here. Using our knowledge from the last unit, subtract those exponents, so we get 24 is equal to 6b squared. Divide by 6 on both sides. 4 is equal to b squared. Take the square root of both sides. B is equal to 2. Now we had a condition where b had to be a positive number. So normally when you're solving a square, you would say, oh, okay, that's equal to plus or minus the square root. But because of that condition with exponential functions, b is only equal to the positive version of that. Now to find a, you take that b and you plug it back into the equation up here. A is equal to 6 over b, but instead of b, we're going to use 2. We find that a is equal to 3. Every exponential equation should have y and x in your final answer. So we keep the y, replace a with what it's equal to, 3, times 2 instead of b, raised to the x power. And this is our exponential function. Now, they may not give you the coordinate points outright. Sometimes they might give you a graph and say, hey, pull 2 coordinates off of this graph and then do this work to write me an equation.